let's talk about harmonics. Suppose I have a standing wave on a vibrating string. So here's my string, and ooh, it's not doing anything. And I give it a pulse, and I give it a series of pulses so that it goes down and it hits the end of the string. When it hits the end of the string, you remember it's going to bounce back on the opposite side, and we're going to pretend like this is a nice even wave here. And if you get the frequencies just right, it's going to produce a standing wave, so that this wave actually looks like it is standing when in fact it's really one wave going to the right and one wave going to the left. You'll see alternating regions of constructive and destructive interference, and it produces a very nice wave shape. The first harmonic for a wave occurs when both ends are fixed and you have one node on either end and one antinode. Now an antinode is up here, N-O-D-E, where the wave is furthest from the equilibrium line. And the nodes are where there is no motion. Nodes are no motion, M-O-T-I-O-N, can't spell. And an antinode is where you have its largest amplitude. Now let's look at this. One wave, a complete sinusoidal wave looks like that. So in a standing wave, it's going to look like this. It's going to have two antinodes, N-O-D-E-S. So this right here, you can see, is only 1/2 of a wavelength. So what I recommend you do is, when you do these, you take this distance right here and you call it L. And you identify how much of a wave do you have. Now, one antinode is 1/2 of a wavelength. So in this case, L is going to be 1/2 of a complete wavelength. And this tells me the wavelength of this wave is going to be twice whatever the length of my string is. Now the second harmonic is when you have two antinodes, and in this case 1, 2, 3 nodes. You need a node on either end, one in the center. So in this case, here's the length of my string. My string goes from here to here, and L is, I'm going to count the antinodes, 1, 2, it's 2/2 of a wavelength, or just lambda. In this case, the length of the string is a wavelength. Alright, let's see if we can do these. If I have the first harmonic as 1/2 of a wavelength, so if I have a 4-meter long string, my first harmonic, you'll remember, has one antinode. So it's going to go up like this. And you'll draw it so that it's accurate. So, in this case, L is 1/2 of a wavelength. So the wavelength is twice the length of the string. The length of the string is 4 meters. So a wavelength is 2 times 4, or 8 meters. What about the second harmonic? Now remember, the second harmonic is going to have 2 antinodes. 1, and this is not going to be very even as it happens. 2. I'm going to complete my diagram here. So this is the second harmonic. Here's the length of my string, goes from end to end. And this length is equal to 2 lambda over 2, because I have 2 antinodes. That's that 2 right there. So the length of the string is equal to the wavelength. So the wavelength is equal to 4 meters. Now, what about this one here? The third harmonic has 3 antinodes. So let's see if I can get these kind of evenly spaced. It's not as easy as you would think. Let's see, it goes up, that's 1, 2, 3. So let's finish this wave out. Gee, you will draw it so much better than I do. The length is the length of the string. So L is 1, 2, 3, 3 lambda over 2. So the wavelength is going to be 2/3 L. Now let's see, the length of my string is still 4 meters. So this is 2 times 4 divided by 3, or 2.67 meters. So right here, this is one wavelength. Now, musical instruments operate with many different standing waves occurring at the same time. Even a single pitch can consist of multiple frequencies. We very rarely hear a pure pitch. Now, the simplest vibration is the first, and it's usually just one antinode. The wavelength to produce the first antinode, the first harmonic, as we've seen, is 2L. Now let's talk about what frequency that is. The simplest, most basic, it's fundamental. The fundamental frequency is the lowest possible frequency. And we say that the frequency, let's see, V is F lambda, so that tells me the frequency is the speed divided by lambda. And since lambda is 2L, the fundamental frequency is your speed divided by 2L. We call this the fundamental. Now, harmonics, as I mentioned, are integral. Integral means 1, 2, 3, 4, 5, multiples of the fundamental. And these patterns that we get, you can see, are called the Harmonic Series, which is an entire branch of physics based on Harmonic Series. So you see there's the first antinode, 1, let's see, 2, and so on. Now the Harmonic Series for a standing wave on a vibrating string is, let's see, the nth harmonic is n, where n is your harmonic number, or the number of antinodes, times v, the speed of the wave, divided by 2, times the length of the string. Now, when a guitar player plays his guitar, he presses down, he creates a node. So this is how they use one string to produce many fundamental frequencies. Now let's review standing waves. One antinode, half of a wavelength, fundamental. Remember, we also call the fundamental the first harmonic. There's one antinode. Second harmonic, 2 antinodes. Third harmonic, 3 antinodes. If I were to count nodes and antinodes, the fundamental has 1 antinode and 2 nodes. The second harmonic has 1, 2, 3 nodes. The third has 1, 2, 3, 4 nodes. So you always wind up with one more node than your harmonic number. Now let's look at the standing wave series. We're going to see if we can come up with a very nice formula. Let's see, the fundamental, n is 1, first harmonic. 1, 2, if n is 2, then F2 is equal to twice the fundamental. Let's look at this. F3, I have 3 antinodes, is equal to 3 times the fundamental. Well, F4, it's quite easy to see on 4. It wasn't quite so easy to see on 3. It's 1, 2, 3, 4. The frequency is 4 times the fundamental, etc. So, once you have the fundamental frequency, if you know the harmonic number, then the nth frequency is just n times that fundamental. Now, what if we're looking for, instead of the frequency, if we're looking for L? We did this a little bit before. Always say L is equal to, and make that the length of your string. And then count the number of antinodes, divide that by 2, and multiply by lambda. So the length of your string is always going to be n lambda divided by 2. Let me solve this for lambda. Let's see, this is going to be, I'm going to come over here. 2L is n lambda. So lambda is 2L divided by n. Let's work a problem. Suppose I have a guitar string, it's plucked, and it vibrates at the fundamental. The guitar string is 0.68 meters. 0.68 meters is the length of my string. What is the speed of the wave if the fundamental frequency is, let's see, frequency 1 is 262 hertz. Now, here's my wave. Alright, and I'm just going to do this totally from scratch. L is 1/2 of a wavelength. So the wavelength is 2L. The velocity of the wave is f lambda. F is 262. Lambda is 2L, and L is 0.68 meters. So this gives you 356.3 meters per second.